In this video, I'm gonna explain how to turn characters and colors into binary and hexadecimals. So I was having this issue with my friends using unclear expressions such as "What up, diggery dog? What's crack-a-lackin'?" So I came up with this idea. I wrote this tool, and it can turn this text into binary. All I have to do is just click there, print, and there. And this is way more comprehensible. So, and I know there's a lot of people out there having the same issue, so I provided the project file in the description. So now let's go into some theory and understand how everything works, and afterwards we'll go back into Houdini and explain, go into the code and explain everything. So why do we need to turn things into binary in the first place? Well, the hardware we're using, it's transistors. It's either on or off. So we only have two options here to work with. So we could encode these as 1 and 0. So we only have two options. And we need to use all the buttons on the keyboard, all the characters, symbols, number, etc., and turn them into these two somehow, like a combination of these two. So whatever A, B, C, 1, 2, 3, etc. need to be represented in ones and zeros. So if we list all the characters, we'll have 128. If we want to use colors like the RGB values, we need around 256. 0 to 255, and the characters are 0 to 127. These are the ranges of the arrays that we fit these in. Why these numbers and not something else? Well, we're using powers of 2. These are powers of 2, so 2 to the power 0, 1, and that's 1, 2. With these numbers, we need to get any value in between that range or that. Let's say I need the letter A, capital A. How can I find it in there? I need it from there. Well, each letter has a decimal number, and capital A is 65, and this corresponds to the index at which it's inside in this array. So if we start counting, let's go to Houdini and see. This is the array, and if we count each element, we'll get to A, capital A. And capital A is the 65th element inside this array. Okay, so this 65. Now, how can we turn this 65 into zeros and ones? We have a method. First off, we check if it's bigger or smaller than to know where it stands. So 65 is smaller than 128, but it's bigger than 64. So it's somewhere in between here. 65 doesn't have 128, so it's a 0 here, but it does have 64, so it's 1. Okay, so 65 minus 64, we still have 1. like 1 doesn't have 32, so 0, 1 doesn't have 16, doesn't have 8, no, it has 1. So 1 minus 1 got 0. So this is the binary code right here. The characters are from 0 to 127, and 127 is less than 128, so we're never gonna be using a 1 here. So these characters actually just need 7 bits, but we add a 0 in the end here, so we would use 8 bits. But the RGB values, they're from 0 to 255, so we will use this. And if we add all of these up, let's say we had 1 here, 1 everywhere, and we add all of that, we will get 255. That's why it's 255 here. And that's 8 bits, since these are 8. But we could have 16 bits and more. Depends on what kind of value, like how many values do we need for the colors. Now let's get into the coding part. First we get the inputs, then we do some operations on them, and finally we print. So first off, I define the character list. That's a channel, so I could type right there. Whatever I type will be turned into an array with refind all. If we see down here, that's the text, and the text AR, that's how it becomes after we use refind all. I need it in an array. I need each character in an array so that I could use find and go back up here and find each character and get the index. So we find the character index and append it. So this text is turned into a string array, and we looped over each element in that string array and retrieved their index from this big array. Now that I have the decimal values, I can start doing this operation that we just discussed, where we turn the decimal number, this 65, into binary. But we're gonna do that for each one of these decimal values. First off, right here, so this line, we evaluate the number between the previous power and the current power to know where do we stand. Then once I know where am I would subtract the smaller one and repeat. And as I subtract, I would append 1 to a new array, the binary array, right here. So we keep doing that until this is filled. But this is like too long that we cannot see it all. So instead I wrote this so we could print it out. First I need to convert the integer array, the binary, into a string. It to a converts integer to string. But I had to use a for each because I cannot just convert a whole array of integers. I can do it one at a time. So I had to use the for each. I'm going through all this trouble of printing a string array instead of integer array so I could add a space in between each binary code of these letters. So here I inserted a space every ninth element, every ninth, because it's 8 bits, so the ninth would be where we place the space. And here I just popped the first one because it inserted a space at the start and I didn't want that. Finally, one last for each to print each single element. Now let's see how we can turn colors into binary then hexadecimals. Let's go to that one over there. For this one I used points instead of detail. In this case I turned the pixel values into @cd attribute and turned that number into a range between 0 to 255, then that decimal value into binary, then hexadecimals. In that case here I used this texture. I got it if we dive in here, I used a file and I got it from the Substance Designer basic textures. I used a grid with a wrangle to fetch the pixel values and put them on actual points. And in this case the grid is 512, so we have 512 resolution. Instead of pixels we have points. In this wrangle I used a color map and I got the file and I exposed the file here so I could change it whenever I want. And this file is referencing the full path of the output, outcops, which is outcops here. And the color map needs a boundary, which is the position on the x and the y axis. And I exposed a tile parameter if I wanna go ahead and tile it even more or less. I noticed something. Substance Designer actually stores, if you see here, they just store their grayscale values in the red channel, just in the red. So I overrode the green and blue channels to be the same as red. Okay, now that we imported that, let's see how we can convert that to binary first. I'm using the same method I used earlier with converting strings into binary, but in this case we're converting RGB values into binary. But here we're converting the RGB, which is 0 to 1 space, into 0 to 255, so we could use it as decimal values. And we'll do the same thing. First off, construct the powers of 2 and know where is the current value sit in between. Subtracted, append 1 if we go into this if statement. If not, just put it at 0. That's how we construct the binary. Now that we have the binary code, we could move on to the hexadecimals. But first, let's check it. Let's check it real quick. So that's the RGB. We got 20, 20, 20. So this is 8 here, 8 bits, then 8, then 8, and they're all referring to these three same values. So let's try and count it the way we did with adding numbers here. Okay, so 20, first off, this first 0 is 2 to the power 0, which is 1. So 1, 2, 4, we've got a 4. 8, we don't have an 8. 16, we have 16. So 4 plus 16 is 20. So that's correct. Let's do that again here. 24, we don't have a 1, we don't have a 2, no 4, we've got a 8. 8 and 16. 8 plus 16 is 24. But if we keep going, that's 32, that's 64, 128. But here we go back to 1 because that refers to the second element here. So 8 bits, then 8, then 8. And so 8 times 3, we've got 24 bits in here for the RGB values. Okay. Now let's see how we can go from binary into hexadecimals. This is the code, but first let's go into some theory. Hexadecimals is just another way of representing these binary values. In our case, we're turning the add CD value that is from 0 to 1 into 0 to 255, as we discussed. That's the decimal, into binary, into hex. So hex here is a range between, like, the range is 16. That's its range, 0 to 15, and that is 0, 1, 2. So that's the range of hex. So on this side it's black, and on this side it's white, and that's the range. So F is white, 0 is black, instead of 1 is white and 0 is black. Now let's take an example to see how we can turn the binary into hex. So let's take the 65 we used earlier. 64, 1, we get 65 because we don't have 2, no 4, no, none of that. Okay, now how can we turn that binary into the hex? Well, hex, we split this into 4s. Each 4 binary digits, we turn them into one of these numbers and letters. So it's in a range of 0 to F, which is 0 to 15. That's the 0th, that's the 15th element. We need a counting system to go from 0 to 15, and afterwards we do the same thing with the index and find the number or letter that corresponds to that index. So that binary, we start off with 1, then 2 to the power 1 is 2, same thing, 4, 8, and we repeat that here, 4, 8. So in this case we have a 4 and we have a 1. So 65 corresponds to 4, 1. Now these are index values, they're not the actual thing from that array. So that's the 4th element. and we count from 0, so 0, 1, 2, 3, the fourth element. And the maximum number we could add is these 4. So 8 plus 4 plus 2 plus 1, which we will get 12, 14, 15. And that's the 15th character, which is F. Remember, here we're not stuck in between 0 to 127. We can play in this range, 255. So let's try and use a bigger number. We'll use 180, for example. So 180, if we want to construct the binary code for that, we'll start left to right because it's easier. This time we have a 128, so that's 1. Now subtract 180 minus 128, 52. So we don't have a 64, but we have a 32. 52 minus 32, that's 20. We have a 16. 20 minus 16, 4. We don't have an 8 because this is smaller. 1, we have a 4. So 4 minus 4, we got to 0, so we don't have a 2 and we don't have a 1. 1, 2, 3, 4, 5, 6, 7, 8. 8 bits. So that's the binary code for the decimal number 180. But now we need the hexadecimal. So the hexadecimals, as we did earlier, it's these 4 and these 4. And they go from 1, 2, 4, 8. 1, 2, 4, 8. Okay, so we have a 1, we have a 2, we have an 8, and here we have a 4. So that's a 4 here, and here it's a 2, 3, 11. Now we got the index values. 4 corresponds to that, 11, 9, 10, 11. It's that. So this is B4. So this is B4. A black value is actually 0, 0, and a white is F, F. Because we've got 1, 1, 1, 1, 1, 1, 4, 4, because it's 8 bits, and those 4 and 4 correspond to 2 Fs. Same here, 0, 0, 8 zeros, and so on. So now that we're done with the theory, let's go back to Houdini. So in here, we're going from binary to hex, and we're referencing this string array that has all the hex values from 0 to 15. First, we take the binary, that binary code, and we split it into 3 different arrays because we're using RGB. I need to evaluate per channel. Then I need to split each of these 8-bit arrays into 4 ones. Every 4 elements I need an array. That's how we add those 4. We need them split into 4s. Even if they were 16, I still need them into 4s. So in here, slice every 4 elements. So that's the binary. And we slice it before and after, which is 4 and 4. And they keep adding with each iteration. So next iteration is 8, 8. And then we split on the 8th. Then inside these 4 element arrays, we loop over each single one of them and take its binary code and multiply it by the powers of 2. So it's 1, 2, 4, 8. multiply it by the ones and zeros, and if it's 1 it'll go through, if it's 0 it becomes 0, and then we add all those multiplications on top of each other to get this final number, either 11 or 4. Finally, we initialize another array and use this summation to reference the hex that's there, the hex array. So whatever summed value we got, we use it as an index to get any one of these and append it in a new array. So that's the hexadecimal array. So in here, so 0 0 0 1, that's 1 here, 1. Then the next 4, 0 1 0 0, that's 1 2 4 8, we have a 4, so that's a 4 right there. And it repeats because we're using the same RGB values, 1 4 1 4 1 4, and this binary will repeat. Here I just printed the thing, but be careful if you're using a lot of points. Like here I'm using 512 grid, so it's 512 by 512. That's quite a lot of points, and if I want to print each of these, it might just crash because it gets really slow after you print a lot of things at once. And if you're wondering, here I'm just these are just for visualization's sake. You could see them, yeah, there. Just so I could test the values. But the first one is getting the pixel values. Yeah, I added the option to go even more or less than 8 bits. Yeah, we can go even more or less. If we go less or... Finally, let's lower the resolution just a bit so we could print this out without having a crash. Okay, lower that. And that's the hexadecimal for these bits. Let's try even more. 64. And it's done. Yeah, so be careful with the printing out hexadecimals for pixel values. But with this one, it should be fine.